we additionally derived effective mass. So now we have more consequences of the band theory. From the band, we are able to determine the bulk velocity. We don't have to draw this. This is just so this is energy, velocity, and effective mass, which we said the second derivative in energy decay. So I can see here what will happen. Here I'll have a zero derivative, but it's inverse. So it means I'll have some kind of divergence. No? Here is the inflection point. It's a bit. And then will be here. What I want to get this part, it's going up, should go down, no? I'm not drawing it right. Let me just check. I think I draw it wrong. Yeah. Because this kind of divergence. Can you see? Because now I put together two things. This is velocity, this is effective mass. And we are getting here something strange for the mass. Infinite. What's the meaning of that?
Again,
I couldn't hear. Sorry. This is an effective mass. It's a derivative of this one and then inverse. So we obtain at pi over half a, 2a, we obtain divergence. And I'm asking what's the meaning of divergent mass? This is coming straight over from the formulas. It's all correct. Okay, maybe I'll let you think about it. And we talk next time.
Crazy, I don't see the divergence.
You don't see?
For example,
here.
No,
Here.
for example, if we take
No, it's zero here. Derivative first. This is a first derivative.
Yeah.
Then you take one more derivative.
Yeah.
It's zero, but it's inverse. So effective mass is 1 over 0.
Yeah.
Okay, now everybody sees
Yeah.
there has to be divergence
Yeah.
at the point of inflection of the band. I'll let you think, and next time we discuss that a bit. It's very simple, but it's good that you think of it. So we continue. Any questions on the transport?
If we take one-dimensional tie binding, the dispersion is -2 cosine.
Yes. Let's
And
say
it
this
means
one.
that the divergence has to be on pi over 2.
Of what? Divergence of what?
Mass.
No, it's in the middle.
Yeah, and that middle point is pi over k equals pi over 2.
2, yes.
Yeah.
Not at the edge of
Yeah, of
so-
course.
So
Ah,
why
okay,
is
okay,
the
sorry.
divergence at the edges is the question?
Not at the edges, in the...
It's in the middle of the Brillouin zone, in at least one
Yeah.
case. I'm not going to generalize this. But it's very easy to get a point. Wherever velocity has extrema, you'll get divergence. Wherever the band has inflection point. It's actually nothing too difficult, but I'll just let you, I mean, it's, we'll discuss, not tomorrow, but on Thursday. So today we will continue with the applications of the band theory. The last part, into optical properties. We will mostly focus on semiconductors, but it's not only limited to that. It's complete. So what happens if you have a material? No, this is not working. And you shine light on it. Anything you can draw that we want, a material, crystal, bulk. I imagine it's big enough to think of the bulk. It's too complicated to think of surfaces. And then shine light. Oi, oi. What is light?
Energy quantum.
Electromagnetic radiation, no? So I can also write the field, electric field. The same thing with the B field, which is orthogonal, no? You know, EB and K. K is the direction of propagation orthogonal. So what happens to this light?
It gets
I
scattered.
Scattered, okay. Through the material or up?
There will be some transmitted. There will be
Yes. Yes. So you will get what you call scattered, I guess. Well, it's good for both. It will be reflected. A small part of it, let's imagine we have a nice surface, will be reflected. Oh my God. This is incident light. Intensity, it's proportional to the square of the field. This is reflected light. Did I call it somehow differently? Which depends on the reflection coefficient, R. Normally it's a much smaller amplitude. And then there'll be a part which is actually transmitted, decaying. The intensity of the transmitted light can be measured out of the sample. And here it has transmission coefficient. You probably know. Did I use the same? Part of it will be absorbed in the sample. So a part is reflected in the same direction, never enters the crystal. Part is absorbed, disappears in the black hole of the crystal, and part gets out. So absorption plus transmission plus reflection should be equal to 1. Well, in principle, one could study all three of them. We don't have time to just have one lecture for all of that. We will focus on the absorption, because it's the one which greatly depends on the band structure itself. Not so much on the charges and on everything, but on the band structure itself, the most sensitive of the three. So we want to see how the crystal will absorb this light, how it can happen. We will work in the perturbation approach, perturbation theory approach. We will consider normal and perturbation, which will depend on the field, on the electric field. So the last few lectures we are just taking into account the electric field. What else I want to say? Yes. The tough part in this lecture, the only tough part I would say, is to actually derive the Hamiltonian. I could just give it to you and we have a lecture of 10 minutes. There is a problem. We have a crystal, we have an infinite system. It's infinite distribution of charges. You put it in the field, in the electric field. It's highly non-trivial to find, highly non-trivial, it's non-trivial to find how to find the energy of that. If you had a system which just has a few charges, you can use energy proportional to the density times, which is actually dipole moment. Am I right? Let me just check. times the field, yes, which you can express just from here. Here you need an integral over the whole space. It won't work because you have to integrate. It depends. There is an R operator, and you have to go over whole space. You assume bulk crystal, which is infinite. So we cannot use just a simple expression which we are used to from some classical mechanics, and we have to derive something which can behave well also in the electric field. For that, well, maybe I noticed that last years this was a bit difficult to some students. Maybe I will write Maxwell equations on the side, that it's easier to follow. You don't have to, you know this, but just to be easier to follow, if I write them, divergence of B is 0. Divergence of electric field is 4 pi rho. It's all in Gaussian. Did you use Gaussian units? For me it was terrible. I always use SI and go to the States, they use Gaussian. I couldn't translate anything. Curl of E. Curl of B. No, this is the current. Plus 1 over C. I think maybe 1 over C is out, sorry, I'm not so sure. Yeah, 1 over C is out. Okay. So we'll talk about the gauge invariance. You probably know the fact that the potentials uniquely define the field, electric field or B field. But the vice versa is not true. If you have a field, it does not uniquely define the potential. You know the concept? Yes? No? Okay. We know that, from this equation, that you can find the potential which gives you the electric field. But that potential is not uniquely determined if you just know about the field. Okay, so let me start writing. I can express the electric field as a divergence of some potential phi. But I can also add to it a part which has a time derivative of the vector potential. My fields are scalar field, potential, and the vector potential. You know this.
Yeah.
This will determine the fields. I can add this part, and I will still satisfy all the equations. You take the curl E, you will get it right. You will just get curl of A when you put it here. Or I could just stay here now and say A0. I have a complete freedom to choose A and phi. This as a concept is okay. And also B. I think I just put okay, so A can be defined. There is this constant F that I can constant function of the space in space and time, which I can vary and not change anything. No, not B, sorry. A can be written. Here I was forgetting. B is curl A as the main definitions. And I can change phi. Not sure plus or minus, I will check. dt. I think plus. So there is this function f, which will be arbitrary, completely arbitrary. Now you can go and check in the Maxwell equations if it changes anything. I just remind you that the curl of divergence of a function is 0. And then if you try to plug them in, that's why I wrote them, it's easier to check. You see that indeed this f is fully arbitrary. Okay. As a concept, I go there. And in this lecture, what is common of this lecture in this derivation is to use a gauge of phi is 0. This is what we will do also. So we can derive the electric field as C d over dta. And from there, actually, and I know the electric field is equal to this, I can also write the dependence of A is full. Well, it's enough to. There are a few ways to do it. From which I will get that B is also 0. But I can also do later, I will plug this in and get a full expression in A. So I can, not so much space. So we are looking for the gauge invariance with respect to the electric field. And I'm going to write the Hamiltonian, which we are going to use. This is just the introduction, and I'll try to prove that it has to be the form that I wrote intuitively. So 1 over 2m can be plus and minus depending how you take the charge. Put plus. Here. How do I prove that this is the right form of the Hamiltonian gauge invariant? Let me try to find the classical equation of motion. This is now a very intuitive approach. This is a force, no? Mass times acceleration, and this is true. Actually, I could also add Vxb, but I'm setting the simple case no B field, just to make it simple. And this electric field in general is equal to this. Minus plus 1 over C so I can move this here plus E over C over dTA is equal minus E gradient of the potential. And here, let me compare it. What I get when I use Hamilton equations on this one from classical physics. You probably remember. You can write it in the terms of Q or R and momentum. So dr over dt is velocity. I think it's positive, do you remember? I have to check. It's all from the classical physics. So I'm deriving direct equation from classical physics. And this will be equal, 2 goes here, 1 over m, pi minus E plus E over CA. Good. Let me go. Let me move this. And I can do the momentum derivative. And that's minus now. This doesn't depend, there is just this minus E divergence phi. Okay. So I'm indeed getting velocity, momentum to be equal to this, which is my starting point, which we knew that I'm assuming it here. But also I'm getting that the time derivative of momentum, which is this, is equal just the same. So it is completely consistent within this simple approach of writing it classically. But it's all coming from the gauge invariance. And this is called P plus E or CA. It's called kinetic momentum. But now we have to take into account also the vector potential. And you will see that in our derivation today of the H prime, which was here, this A will be crucial. It's the operator which we lacked. So this is the A of the light. Yeah? You understood that? This A is determined by the light you're shining. Any questions? When there are no questions, it's either too trivial and boring, but it was so difficult that you couldn't get anything and not ask a single question. So I don't know which one. Which one I want to hear is the answer.
Actually, you said that A is correlated with the light moving poles.
Sorry?
The A that you
The
just
vector,
read.
this one
Yeah.
or this one here? This one?
This.
Yes?
And that is correlated with
The light.
The light.
Yes.
How did you?
It's determined by the light completely. From the fields, from the E field and B field. It's coming from there. Because curl A is B. B field. And B and E, you have them in the radiation together. But also through here, no? Also through here you see that both of them are determining. I'll just keep the Hamiltonian. So it is the only choice for the infinite system, this Hamiltonian. Okay, let me write it out. This is the first, the full Hamiltonian. This pi square and E pi are going into A0.
Which states are we going to up this Hamiltonian? To the light or to some?
No, the crystal.
The crystal.
Crystal states, the block states.
Okay.
The block states of the crystal.
And also we said earlier that the potentials cannot be uniquely derived from the fields. We are given all the
They cannot,
fields.
yes.
So how are we going
And
to
we are
choose
going
the
to
A?
use, okay, I will just set what I put maybe too fast. You can see here, pi 0. Let's call this V because this is now confusing. a V, I will put phi 0.
Ah.
This is the Weyl gauge. I didn't, it's not so important that you go on that, but we'll use it in the further. So to keep our life simple, we will actually just take into account the first order terms in A. They're more significant. And disregard A squared. You get a bit of corrections. So this is the part of H0, and this is the H prime. My H prime, that is E over 2 MC. Actually, it is time dependent, no? You can write it. It has time dependence from the A. And A is actually determined from the E field. So if electric field is 0 times E k R minus omega t, then I can say that A here from this. It's good it's not removed completely. I can still use the equations I raised now. You all see this one? I don't have to copy it. From here, I can determine the A such that the derivative in time of A gives electric field. So you correct me. And there is a C. Omega I should be down, no? There is an I, and then there is E. Let me check, I don't want to. And there is a minus, yes, there is a minus, because here it's a minus. Okay, let me write here the whole thing, so that you see the dependence. You all see how we got from electric field, we got vector potential. Using the gauge at phi 0. Okay, one layer I think it's fine, but second layer I won't be able to use the.
At this point we can also add some constant vector to A.
Yes, yes.
But we just don't.
It is this F. It will be the F that you can add.
Yes.
You remember?
Yeah.
I know
yeah.
You can see here. That was the. It should be the gradient of something.
And we don't do this.
We don't do this. It's actually relevant.
Yeah.
If you add a constant, it won't change anything. Okay, so let's write out this fully. No, actually before I wanted to say something before I go to derive. Yeah, but I need to keep this written. So what we want to actually derive. We want to see what happens in the bulk crystal when the light shines on the crystal. And let's see the example of beryllium. It has 4 electrons. I2s2. So what is the atomic? One S, 2S, 2P, 3S, more or less. So this is occupied fully, and this is occupied fully. When you give light, you can excite these electrons. It gives them energy to go into a higher energy state. You excite them. Actually, we can again use the. You have to find transition. This is now atomic case. Atomic transition that you can define as initial, state initial, times the perturbation, which is this part, times the final, or whatever you can actually change. This is a more common way of writing. Probability times the density and the delta functions. delta function, that the level final minus the level initial, this is the energy of the levels, the difference times the energy obtained, gained by the light is equal. No? These two equal. You understand? Now this is the basic principle of the energy conservation. I went a bit fast, but I think it's what you all know. And in the atom, what will happen?
So
Yes.
this rho is
How many states you have? It's a bit trivial in this case, yeah.
Density
how many
of states.
Yeah,
Okay.
but how many states you have, it's well defined here. So this is not of interest in this case.
okay.
It's the, this I can actually remove. It's the delta function,
Yeah.
which is crucial. And what can happen? The lowest energy to excite is from 2s to 2p.
Yeah.
That can happen. But can I excite from 2s to 3s?
Yeah.
Maybe. Yeah.
If the energy is...
No, you cannot. There is additional exclusion, or how is it called exactly? I forgot the name. But you can do it only if delta L, which is quantum number, differs by plus or minus 1. So you can get atomic transition to a state from S to only P. From P to S or to D, not to P. This isn't yet deriving quantum mechanics or
It's Hund's law or something.
This is not the Hund's law. I don't think. Yeah, I can check a bit more how it's derived. I thought that you all knew it, so it was not. Normally people say yes, yes when I mention this. So from 2s I can have to 2p transition. The next one would be, I guess, from 2s to 3s, then from 1s to 2p. I can write what I actually obtain if I have beryllium atoms and I perform experiment on them. What kind of absorption spectrum would I get? So the first one, the lowest one, so this is absorption. How they measure it? Probably the easiest way is to measure it in transmission. You check, you know how much light you put, the intensity of light, you know reflectance properties, which are usually very small, and you see how much light is coming out. And then absorption is just whatever is not coming out, it's absorbed. So here is 2s to 2p, you will get a peak. Normally it's not a sharp line. It should be, but in measurements you always have some broadening. The next one would be, it is this one. The next one would be, I think, 2s to 3s. And then 1s to 2p, and so on, until at some point you reach a continuum of states. There is no anymore discrete levels. The levels are so dense that for whatever intensity you put, energy, you get out something. And it's all very clear for the atomic case. I want to derive something similar for the crystal and see how. First, yes.
The delta L for 2s to 3s is it 1?
No, sorry.
Yeah.
No, sorry. I was just writing the opposite.
It's inside your bag.
Sorry.
Yeah.
Well, it's a lot to think. Sorry, it was wrong.
1s to 2s on the top. Not 2p.
This was correct. 2s to 3p, 2s to
Wait,
2p.
1s to 2p.
Yes. Yes. The orbital quantum number, L. N doesn't matter.
Okay.
Just the orbital number. You know the L, no? I am assuming that
Yeah.
S is 0, P is 1, you know. No? Okay. At this point, I should mention you get photoionization. You're actually able to throw the electron out of the system. This is photoelectric effect, no? You know, it's much easier, I mean, it's easier in the case of atom, because in a crystal you also have work function. You remember these things from some physics 001 a long time ago? It rings a bell.
What name did you say?
Work function.
Ah, work function.
Work function, yeah, you remember, no? It's a but now just think of the crystal. You don't have these discrete levels. You have bands. So it is not so clear how will I excite electron from, let's say, occupied part to empty, from this state. It's not obvious. So we will derive it now, what I wanted to do a few minutes ago. So I have my vector potential, I have my perturbation, and I also need block states. Block states, I will write as E under KR, and the Fourier transform over G vectors. I can do it because it should be U here, but I can write to make it simpler in 2 steps. Managed to use the same. Is it okay? You all see it, no? It's just writing it. So, I'm trying to find matrix element width of this H prime. Final and initial. And to tell you right away, I won't really find the element, the main element completely. It's too much work. I'll just find the condition when it's non-zero. I think it's enough. So let's write carefully. D3R E/IKR sum over G. Actually, it is all. This one is entering as a conjugate. G E minus I GR times. I can put this out to MC. A is this. More constant, Ci omega. E0. Times E under I KR. Sorry. This I have to call final. This is K final, I'm calling. And the K is the wave vector of light. Minus negative times P. Now let me just break it for the first part. I'll just do the first part and then it's the same thing for the second, because this is lots of writing already. Here I have plus IKI R, the sum of G prime, Fourier coefficient, plus one term. Let's make it a bit simpler. Okay, now let me put together all the exponents, all the exponential functions here. So I have E on the minus I K F R, E on the minus I G R. Actually, there is no this thing anymore. We are inside the integral. GR, E on the I K R. You can put here omega T. KR, I K I initial R, E I J G R times something else, and the similar integral. Okay, you all understand what I just did here. Just put together all the exponents with the spatial expanders.
And the summation was taken out by the UG prime.
Yeah, you're right. Yes.
Then with the G prime there.
Any more mistakes? Here I have something which will give some non-zero term. Here I have to get the right condition on the exponents. They have to be equal to
Momentum conservation.
yeah, I'm saying, when will this integral be non-zero? Because, I mean, these all guys are periodic.
Yeah, if this thing is 1, it has to be delta function.
Yes, okay, I'm talking about the, okay, let's write it like this. K F minus G should plus K
Plus K.
plus Ki plus G prime.
It has to be 0.
0. Okay, this I wanted to hear. For this integral, whole thing to be non-zero. Then I don't care. I mean, this will determine the exact how big it is, but this will set the condition to make it non-zero. So K is the wave vector of light. We're talking about optical light, visible light, which has the wavelength of roughly lambda visible, 6 meters, minus 7 can be still. And the K is proportional to pi over lambda. Ki and Kf, they enter through block functions. They're just the vectors within a Brillouin zone. So they have a typical this is the largest actually, 2 pi over A. A is what? Nanometers or angstroms. can be even minus 10, a few angstrom. So the distance between these two, or these two, is around 1,000 times. At least 100, but a few thousand times. So in the simplification, I will forget about the k vector of light. It's too small. That okay?
Yeah.
Because it's roughly 1,000 times smaller, for the visible light I'm talking. 1,000 times smaller than the vectors within the brilliant zone. So I'm getting a condition that Ki minus Kf should be equal
G minus G prime.
there is something yeah, okay. No, it's just the opposite. This is the condition I got. Now, what does it mean?
Means
That
the difference in the energy should be a reciprocal.
we don't have free plane waves, so this is not exactly the energy. You know, these are two vectors in the reciprocal in the brilliant zone. Let's go to our grade 1 example. So this is the brilliant zone, and this is the edges. I mean, of course, it's true for any dimension. It's just easiest to show. This is a difference of the two vectors in the brilliant zone. Anywhere you take them, can be anywhere, but they should be equal to the difference of two g vectors.
It means that if the initial vector is in the first Brillouin zone, the final has to be, roughly speaking, in the next Brillouin zone.
Okay, I think that you're on the right path, but so what is the minimum g vector in 1D?
2 pi over a.
Exactly this.
Yeah.
Exactly this.
For example, if we take g prime equal to 0, then it means that after the scattering, this state will be transferred into the next
But
Brillouin
these
zone.
two guys are within the first brilliant zone.
Both are within the first
Yes,
Brillouin
I mean
zone.
this is the definition of the
Ah,
Bloch
yeah,
function
yeah.
that we always use. So this sounds a bit. They both from the first brilliant zone.
Yeah.
Anywhere. And the smallest g is equal to pi over a.
Is it possible?
So they should just move with, from one edge to the other edge, is it?
That could be a solution, but I mean ki can be anywhere. It cannot be that you have transition only at the edge now. It's a bit.
If we try to...
But what is
So
okay?
g minus t should be equal, should be 0?
This is it. I said the g, the smallest g is 2 pi over a, but if they are both the same, it's 0. And that means that ki should be equal to kf.
Yeah.
So I cannot go from here, take a state, I'll draw again, a state from here and end up with a state from here. No, they have to be the same. And this is known as vertical transitions. Maybe there, I can remove this part now. Vertical transition. So now band structure. Whatever. Roughly. It means like if we have Fermi energy here, these states occupied, I can go only vertically up, keeping the case same. This is the simplest case. This is what happens most of the time. And there are slight variations, but we won't consider it. Everything we will consider is just the vertical transition case.
If we apply this thing to free electron model,
Yes?
then this condition, does it say?
I think it doesn't change much. It doesn't depend. The derivation is quite general.
Yeah, it's general.
We just assume Bloch states, so anything quasi-free, let's say, and the vector potential of a certain general form.
Is it that equation ki minus kf equals 0 is just the same thing as, for example, if you, for the final you have this g prime, but you can just translate it back inside the Brillouin zone. That's why it's like a vertical transition.
I mean, you can also look at it and the extended zones.
Yeah.
You can, yeah, but I think it's more confusing because it anyway has to be the same state. You just have to shift it here.
Yeah.
Yeah.
It's the same state, so let's not confuse. Somebody might misunderstand that.
But if we focus on free electron model and we draw it on an extended scheme,
Yes.
then this condition actually shows the same as this one.
Yes,
Yeah.
yes, yes. You
Yeah,
can.
that's
It's the same look. I'm
Yeah.
just looking at it
Yeah,
in two
yeah,
schemes.
yeah.
Yes.
So what's Essence question?
I mean, he was trying to look at it in the extended zone scheme.
Okay.
But I'm saying it's the same thing
Yeah.
because you will always have the same vector, no? Always be this
Yeah.
this vector plus 2 pi over a. Now you can do it. Okay. And how will the absorption spectrum look like? Because I'm not specifying which Ki it should be. I'm just specifying the energy. The light comes with a given energy. So for certain energy, I can have a few transitions. Can have from here to here, and then also from here to here. It might be somewhere more if the bands are less symmetric. From this one maybe to this one, depending on the L. I'll have a few of them. I'll try to draw, yes.
So this is for visible light.
Yes, but it's actually for quite a big range because A is 10 minus 9 minus 10 angstrom. So this can even be smaller, minus 7, even minus 8.
Okay.
It will be up to 1%. And
Considering the L, if the lowest band is completely occupied,
yes,
that's
good.
Yeah, that's good. Due to L,
Delta L, yes.
yeah, delta L, can the like whole electrons on the lowest band excited to fill up the next band and they leave the bottom one empty?
You see, it is very unlikely because you don't have bands flat.
Yeah.
So it depends on the energy you're putting. And you see that they all need different energy.
Yes, but due to L, every transition from the lowest band to the top band for every K is allowed.
Yes,
Okay.
but not for the energy. I mean,
Yeah, yeah,
you need
yeah,
also
yeah,
energy
yeah.
condition. So it's very unlikely unless you have
Yeah.
flat bands. Yeah, so I was going to plot the absorption with energy for a crystal. So now you see it's not going to be so discrete anymore. You can have many more. And the smallest energy at which you can have
Gap.
at which you can excite electron from occupied to empty is exactly equal to the gap,
Yeah.
energy gap. So this is the E gap. So until then, nothing. I cannot have any excitation. But then I have quite a few. I have here 1 or 2. They're not very symmetric. I have here. So it starts as a continuum. Because there are so many states and you have a broadening in the experiment. It's very hard to measure sharp lines, a background. Again, you will have photoionization at some point when it reaches continuum. But here I assumed one thing. I assumed that the maximum of the valence band and the minimum of the conduction band is the same K. But that's not most case. It can occur, it does occur, it's in many cases. Gallium arsenide and similar.
At the energy which is equal to the gap energy,
Yes.
doesn't the absorption spectrum, doesn't it have to have like a huge peak
Why huge peak?
if the band is full?
You're confusing. The band, you're talking about states.
Yeah,
There are states here, my state. I mean, these are all small states.
yes, but the density of states is huge there.
It has to be at the K. It's not just at the energy, it's also at the Ki.
Ah, yeah, yeah, yeah.
This is, I shouldn't have drawn the density of states, it's too confusing.
Yeah.
It's just that this Ki, I have state or not,
Yeah, okay,
don't have the
okay,
state.
okay.
So that was a mistake to write, please erase that. So I can have a different case.
I have a question. With this, if the energy is big enough, the energy you are
Yeah.
giving it is
Yes,
big enough,
in light.
you will be able to get absorption past visible radiation.
You're concerned with that. Well, it depends what I want to do. Let's say I'm doing experiments with visible light. I have such a photon source for visible light. You can have X-rays. You can have many things. And it doesn't change much, by the way. It doesn't change much, the whole thing. You can still survive in the picture of vertical transitions as a dominant process. So I can have, let me call this EF, and then I draw something, and then more or less. I'm always trying to draw silicon band structure and I never manage, so I don't dare to call this silicon. But silicon is a famous indirect semiconductor. So, for the case where the top maximum, okay, if maximum K maximum of the valence band, okay, it's not difficult. Maximum of the valence band is at the same K as the minimum of the conduction band then it's a direct semiconductor. In this case, this is not true. This is the, well, what I'm drawing, of course, assumes this is the lowest part in the whole band structure, and this is the highest. In silicon, it occurs between gamma and X. But this doesn't quite look like silicon. I'm not able. So the maximum of the valence and the minimum of the conduction are shifted. And this is still the gap energy. The shortest distance between the two is the gap. But however, when I shine the light of this energy, nothing will happen. Because I cannot have a direct, from here to here at the energy E gap, not from here to here. The smallest one I can have, find it in this picture, is something like this. So at this K, this is K of the smallest transition, the smallest energy. So again, the absorption spectrum versus energy. And here is the E gap, but I have nothing there. I will have at the so-called optical gap. Optical gap. I'm starting from there until ionization. So neither of them has to be at the band extremum. But then what happens? Okay, I will excite an electron from here to here. So I will create a gap, a hole here, a state here. What will happen is that this system, first, the electron is not in the minimum energy. It will immediately scatter to the minimum, so come to the minimum. Is the time scattering, what was it, 10 minus 14, can be even 16 seconds. Also, this hole will go to its lowest energy position, which means here. This is a relatively fast process. But then you have electron and its hole, and the hole doesn't have to be its hole. And they bind together in a quasi-particle. Have you heard of these things?
Yeah,
exciton. They form an exciton. So an electron here, well actually, all the if they are moving, I know how to exciton. Depending on the system, they can have different lifetimes, different properties. If it's in a metal, if it's in a semiconductor, if it's in an insulator. The point is that it will release energy, this exciton, and it excite something in the system. But at the same time, it will emit light. It can emit light. It can be absorbed and excite phonons, but some will emit light. And they will emit the light at E gap. So in the emission, this is absorption, but in the emission, you will get a peak at the E gap. And this is a property of the luminescent materials. It's called luminescence. And it's used, actually it is used in devices. I think it's called light emitting diodes. Just that there you wouldn't use really indirect gap semiconductor. It takes too much time. You can have it more efficient if you have a direct gap. You form it and you get it immediately. But here this illustrates the principle that actually it is possible to emit light at the gap energy, even though it's an indirect semiconductor. Just right here, this is called indirect semiconductor.
What happens to the extra energy?
I'm saying it can be just emitted, that you get it out, or it can inside the crystal excite something. Excite a new transition or excite a phonon vibrations that we'll do next week, Thursday already. So. Any questions on this?
Exciting the vibrations roughly speaking, means heating up the lattice?
Yes, yes, yes. You cause, I mean, we'll talk about it on Thursday. You cause the atoms to move. There are certain modes of vibrations, and it can excite a given one mode at the right energy. But okay, if you don't get it all completely now, it's fine. It's not yet.
Maybe I don't get this very well. The emitted photon happens when the minimum and the maximum, like the energy difference, is less than the energy that keeps them at their places. They don't go back. They just emit because it is extra energy.
Yeah, because I mean you have an electron-hole pair, which kind of annihilates each other and creates energy.
Okay, so they do annihilate each other.
Well, this is a rough way of saying. I mean, it's not. I shouldn't use this this language.
They kind of go back to their
yes. But they don't go the same way they came there. This is what I wanted to emphasize. They go from different Ks.
Okay.
Any questions? Okay, I think we finished this.
So the energy released by the exciton is not necessarily from the excited electron falling back into it. It's another electron can fall into the excited.
Sorry, you said. I mean, it can be a second excitation that happens. That's what you're saying.
There's one electron up here, and then there's a hole down there, and then they are sort of bonded, and that's the exciton.
Yes.
So can another electron fall into that hole created by a different electron?
Sure, it can happen. I mean, no, I mean, does it have to be exactly the same pair? But there is no name to it. I mean, it's, okay, so one more thing I want to tell you today. It's about the color. Show me the picture. Maybe, but a nicer picture. This one I don't like much.
And so, what if the E optical was 2 times the E gap or more? Would they emit photons and stay at their places, or would they emit 2 photons and go back? Do they need to go back? This is the question.
No, you can have them, but they all have lifetime. You know, they're not infinite. It's not such a long lifetime. It depends on how they are created. I mean, if they are charged, I mean, in a system which is charged or not. In this case, it's quite a short lifetime actually. No, actually, I think it's quite long in this case, in comparison to some other.
Can they emit more than a photon?
I mean, yes, I mean,
But
there
it
is
should,
no limit on the intensity of the.
but it should be also satisfy the conservation of energy.
Sure, of course. But she's saying if the optical is very different than the gap,
Yeah.
then you have like.
So in this case, there was a momentum difference between a hole and a particle. So initially, if we choose a k vector of light that will be specifically this thing, will it work directly?
Okay, you want a k vector of light, so you're not anymore into visible light, no?
I'm into visible light, but the energy of the visible light is
the energy.
E-gap, is
Yes.
E-gap, and the momentum of the photon is exactly this momentum.
If I had E gap in this case, and I do absorption, I get nothing. That's clear, I hope. I mean,
For any k vectors.
yes. You get this only in the emission. It's impossible. E gap is the smaller than the minimum vertical difference between the bands. The minimum is optical gap
So,
difference.
Here's the thing. To have this kind of straight transition from the maximum of the bottom
Yes,
band
here.
and minimum of the top band, there are two conditions that has to be satisfied. One is energy conservation and one is the momentum conservation.
Yes.
At this point, the momentum conservation is not satisfied.
Yes.
That's why it doesn't happen.
Yes, exactly.
But if I choose the K vector of photon, fine tune
It won't be.
it won't be still.
It won't be invisible light for sure.
But it's possible.
Yeah, I guess up to a point. To a point. Yes.
No, he's talking about the
Yeah.
energy. The
You
energy
want
of
to
the
change
photon.
the K, but you don't have any more this condition. So you have to put the K.
Yeah, also the K.
Yeah. You have to here, whatever. You put the K, which has to be so large.
Yeah,
I mean, one has to find what should be this K.
it has to be really small. So basically it means that if this is the crystal and I'm shining the light or whatever it is in this direction,
I
there
mean,
is no absorption.
It is possible to have indirect transitions. I just don't want to confuse. We are now staying in the visible light regime. It's not impossible. I'm saying it's in this condition that it's
Yeah, okay.
all in solution. But it depends also how much you want to do. If it's just a little bit from here to here, it's very likely. Depends. Now you reminded me about the photo emission. I'm not sure you guys know about it. Let me go back. That's not something I plan to talk, but it actually depends a lot on the light you have. If you, for the photo emission, which is actually a very similar process, you shine the light, you take an electron from here, you send in the higher state. If you have a small energy radiation, like UV, ultraviolet, we are here. It is extremely important, the states that you are sending. It's known as the final state effect. It completely depends on the band structure. It's completely, I showed it now, determined. You have a little bit different dispersion, you lose photo emission. However, if you have X-rays, which what is thousands of times more energy, you will actually go into continuum state. You will be able to go from here to the pure continuum. And you don't actually anymore feel the difference of the bands, dispersion. You are much, much, much less sensitive to dispersion. So only in this limit of UV light or visible light, you're extremely dependent on the so-called final state effects. And this is the limit that we are doing today. What I did want to say, actually, was again about the visible light. Let me copy the violet, blue, green. Then orange and yellow-orange. And red. Now, the energy of the light roughly, I think this is from 1.7, this is to 2.7. Bless you. I think, no? Yeah, more or less. Then you have infrared and ultraviolet. So, what happens when you shine the visible light to a semiconductor which has a gap smaller than 1.7 eV? So let's say this gap is silicon or whatever, 0.5 eV. The likelihood is that
it will slightly
Excite.
condensation.
said that all the light will get absorbed. This means light is absorbed. When it excites, it means that the crystal takes and absorbs the light. All light absorbed. and the material, the crystal, appears opaque. So this is true for all the semiconductors, but also for metals, which reflect also. And what if the gap is larger than 2.7 milli? I mean, this is roughly 2.8, 2.9, it's all there, of course. I mean, this is just the... So you have a large gap, you're shining light, which has this much energy.
No transitions.
All the light is transmitted. Transmitted. And then, if it's in between, if the energy is in between these values, this is interesting part. The gap is 2 eV. And the energy, sorry, the energy, no, right, the gap. The gap is 2 eV.
The ones transmitted are the ones the color.
Sorry.
The wavelength that can be transmitted are the ones which determine the color.
Yes. Amel just gave you the answer. So depending on which part is absorbed and which part is transmitted, the transmitted part will define the color of the sample. So there is rubies, no? Like this dark red color. It's coming from there, from the gap properties and the band structure. Did you understand? This is true also for the direct and indirect. You just have to write a bit the condition. It holds true. Any questions? I mean, this lecture today actually is what some people work whole life on. And many of us in condensed matter are somehow related to this. There are many experiments, lots of research in theory.
What
So
is
this
it
is
called again?
Hmm?
What is it called again?
What?
You said this.
Optical properties?
By color we mean that the sample is transparent.
Yes.
Yeah.
Yes, transparent, yes. In this case, transparent. Actually, I should write this. Transparent. Do you know any transparent? Yeah, it has a huge gap. I forgot. Yeah. And then you can put also the impurities, which have a certain gap and which can absorb the light. So you can put a very small concentration of an impurity which has certain gap, it will change the color of the crystal, the whole material, even a small amount. Okay, I'm done. Any questions? I think it's good for you to ask questions. Then, I mean, you solve problems that you don't have to solve later alone when you're studying. But I know also it's very early for you.
What if there is no gap in the band structure?
It's a metal.
It's a metal, and
Yeah.
the color of metals, like
They're opaque. They're opaque. They don't have really some color.
yeah, but what about gold and copper? Why do they have that color? I always wanted to know that. I have no idea.
Let me think a bit. I did not think of gold and copper. But I think it's the reflectance properties.
Yeah.
It's not on the absorption, it's on the reflectance, yeah. because it's much more important for the metals.
But it reflects yellow. It reflects yellow.
I think it's on the
There is
reflection
some
coefficient.
absorb. There will be some absorbed.
It's the reflection coefficient, which are more important in that case. They reflect, yeah. It's not absorption because it's not, everything can only be absorbed, but there is a big part of reflection actually.
I have one more question,
Yes.
but we raised the equation for it. For this
Yes.
this transition, there was 1 over omega.
Yeah, this was coming from the A.
Yes, and all the other terms that was after the integral.
Yes.
Do they cancel this omega or not? Because if we take omega to 0, what it means that we are shining a static light or whatever. No, not static. I mean really low.
But, I mean, as long as you have field, electric field, it has to have omega.
If it's really
If you
small.
have electromagnetic radiation.
Yeah. If omega is really small, it means that the frequency
I mean, that you are in a very, very
short.
low energy. You don't excite anything.
Yeah, but this 1 over omega thing, when omega is small, is getting big.
But you won't ever reach the energy condition or anything. If you go to tiny, or the semiconductor, I mean, talking about the gapped systems. I mean, as soon as you have the radiation, you have omega.
Yeah.
Now, being small or big, it's a different question, but it cannot be 0 exactly.
Yeah, of course.
But very small, anyway, if the whole thing is 0, you can put whatever coefficient you want in front of it. I think. Now, do you want to leave or you want to continue with? Yes.
For the materials with the energy gap greater than 2.7,
Yes.
we said that since there is no possibility of the absorption, as you have said,
Yes.
and we said that those light will transmit it.
Yes.
Why only transmitted? Because there may be the probability of reflection.
Okay. I'm saying for the light which can be absorbed by I mean, there is always a reflection part. No, there is always a reflection part in that. And it depends on the crystal, on the system, yes. This is just the
That
generic.
means for the
but,
gas greater than 2.7, there may be the transmitted
but,
wave and reflected.
Absorption is not going to occur. So you have T plus R equal 1. That's of course, yeah.
Does the emission have any contribution to the color of the crystal?
What do you mean?
When you absorb a photon and then you emit in a different wavelength, does that
This thing, yeah.
does that make any contribution to the color of the crystal?
Can it be anything?
What is the color of silicon?
Well, I don't know. Well, it is too small, the gap, 1.1.
Silicon metal has a metallic color. Not metal, I mean the silicon element has a metallic
it's
color.
a semiconductor, and it has a gap below this range, so it shouldn't pick. Your question? Actually, it matters whatever light comes out. So you're saying that you would actually emit, if you emit, I mean light can be also absorbed inside, no? Light transmitted. I'm not aware of, but actually, yes, if you know, I mean photoluminescence, this it's also called photoluminescence in some cases. It gives color, yes, exactly. It gives, this is the process which gives color. And there is this particular color that can be given exactly, yes. This process can give very specific color depending on the gap energy.
Okay. That's why when we put impurities, it changes the color of the crystal?
Not just that, I mean in general. impurities doesn't have to be from the excitons. They can be absorbing on their own. They change the gap. They can change the gap. Okay, actually, it does change the color, right? But I didn't mention this. It's a very typical light, typical wavelength. Any question? The more interesting questions, I really have to think.
Is there any subtle reason why gold and copper are like yellow?
We just discussed that. I don't know the reason right now, but I would guess it's because of the reflectance properties. It's not due to absorption, but due to reflectance. But I can make sure. I don't want to say something stupid.
It's a stupid question because I did the example of luminescent material is, for example, luminescent diodes, right?
Yes.
And one of the basic examples of luminescent diodes are very common is Christmas lights.
Okay, yes.
So what happens is that when the Christmas light is changing colors, the emission part of the ECAP is changing.
What? Really?
Because the emission part of the ECAP is changing to 2.7 dB to 1.7, that's it's changing colors.
And how is it changed? Being changed?
I don't know what is being changed there.
No, actually, there has to be 3 different crystals of semiconductors. Shouldn't it? Because if you just pass the current through one semiconductor, it cannot emit. Okay, say like, okay, I'll emit blue now.
The question is how it's changed. I mean, there should be some change that you, divert in different direction.
How are we changing the emission?
I don't know how it's done in the Christmas light, but there must be some way to. You cannot change the material like that. I mean, it's might be. This is curious.
One more question.
Yes.
If we have 2-dimensional crystal,
okay.
Let's generalize to 2 dimensions. And on kx direction there is a gap.
Yes.
And on the ky direction there is also a gap, but smaller.
Okay.
So is it possible that the crystal will be for certain wavelengths, the crystal will be transparent in this direction, but not transparent in this direction? For certain energies.
It has to be highly asymmetric crystal.
Yeah.
To have significantly different gap.
I don't know. On kx.
It can be in 3D also. I mean, it's not important to be 2D. I think we are done anyway.
Yeah.
So,